This is part 3 of lecture 1.2 of Math 23, Limits and Continuity of Functions of Several Variables. In this video, we will learn the definition of continuity of a function of two variables, as well as the different types of discontinuities. You are expected to have finished viewing parts 1 and 2 before proceeding with this video. We first recall the definition of continuity of a single variable function. A function f of one variable is continuous at a point A in R exactly when the following conditions all hold. First, f is defined at the point A. Second, the limit of f as x approaches A exists. And third, the limit of f as x approaches A is equal to f of A. Visually, these conditions mean that the graph of f corresponding to an open interval containing the point A is an unbroken curve. F is said to be continuous on an interval I if it is continuous at all points in I. If f is not continuous at a point A, then two things may happen. First, the limit of f as x approaches A exists, in which case we say that f has a removable discontinuity at A. Visually, this means that the graph of f corresponding to some open interval containing A is obtained by taking an unbroken curve with a point corresponding to A either deleted or moved to another location in the same vertical line. Second, the limit of f as x approaches A does not exist, in which case we say that f has an essential discontinuity at A. Visually, this means that the graph of f on some open interval containing A either is obtained by taking two curves which approach different points of the line x equals A, or has the line x equals A as a vertical asymptote. We now extend this to functions of two variables. A function f of two variables is continuous at a point AB in R2 exactly when the following conditions all hold. First, f is defined on the point AB. Second, the limit of f as xy approaches AB exists. And third, the limit of f as xy approaches AB exists and is equal to f of AB. Visually, these conditions mean that the graph of f corresponding to some open disk containing AB is an unbroken surface. F is said to be continuous on a region D if it is continuous at all points on D. If f is not continuous at a point AB, then two things may happen. First, the limit of f as xy approaches AB exists. In this case, we say that f has a removable discontinuity at AB. Visually, this means that the graph of f corresponding to some open disk around AB is obtained by taking an unbroken surface and either deleting the point corresponding to AB or moving it to another location on the same vertical line. Second, the limit of f as xy approaches AB does not exist. In this case, we say that f has an essential discontinuity at AB. Visually, this means that the graph of f corresponding to any open disk around AB is not an unbroken surface and cannot be obtained by simply deleting or moving a point from an unbroken surface. There are many ways for this to happen. We shall not focus on these here. Let us consider some examples. First, let f of xy be equal to 2xy over the square root of x squared plus y squared whenever xy is not the origin, and equal to 2 when xy is the origin. We claim that the limit of f as xy approaches the origin exists and is equal to 0. Let epsilon be any positive number and let delta be 1/2 epsilon. Assume that the square root of x squared plus y squared is less than delta but greater than 0. Then xy is different from 0, 0, so f of xy is 2xy over the square root of x squared plus y squared. Using algebra, we can show that the value of the absolute value of f of xy minus 0 is less than or equal to 2 times the square root of x squared plus y squared, which is less than 2 delta, which is equal to epsilon. We will not go through the details of this argument. If you wish, you may rewind to this slide and pause to learn the details on your own. This shows that the absolute value of f of xy minus 0 is less than epsilon whenever the square root of x squared plus y squared is less than delta but greater than 0. Hence, the limit of f of xy as xy approaches the origin exists and is equal to 0 as claimed. Observe that the value of f at the origin is 2, which is not equal to 0. Therefore, f has a removable discontinuity at the origin. Next, let g of xy be equal to the natural logarithm of x plus 1 over x squared plus y squared whenever xy is not the origin, and equal to 0 if xy is the origin. We claim that the limit of g as xy approaches the origin does not exist. Indeed, let C be the x-axis. For xy arbitrarily close but distinct from 0, 0, g of xy is given by the natural logarithm of x plus 1 over x squared plus y squared. So the limit of g as xy approaches 0, 0 along C is equal to the limit of the natural logarithm of x plus 1 over x squared plus y squared. Since the equation of the x-axis is y equals 0, this is equal to the limit of the natural logarithm of x plus 1 over x squared plus 0 squared as x approaches 0. Note that this is a single variable limit of indeterminate form 0 over 0. So we can apply L'Hopital's rule, which you learned in Math 21. This gives us the limit of 1 over x plus 1 all over 2x as x approaches 0, which is infinity. Hence, the limit of g as xy approaches 0, 0 along the path C does not exist. Therefore, the limit of g as xy approaches 0 does not exist. As xy approaches 0, 0 does not exist as claimed. Hence, g has an essential discontinuity at the origin. We now give some results that are useful for determining the continuity of functions which are obtained from other functions that are known to be continuous. If f and g are functions which are known to be continuous at the point a, b, then their sum f plus g is continuous at ab. If f and g are continuous at ab and g of ab is non-zero, then the quotient f over g is continuous at ab. If f is a function of two variables which is continuous at the point ab, and if g is a single variable function which is continuous at the number f of ab, then the composite function g of f is continuous at ab. Recall that g of f of xy is obtained by replacing all instances of the variable in g with the expression for f of xy. As a consequence of the previous theorem, we know that a polynomial in x and y is continuous at all points in R2, and a rational function in x and y is continuous at all points in its domain. For example, the function f given by f of xy equals x squared minus y squared over x squared plus y squared is a rational function. Thus, it is continuous at all points in its domain, which is the set of all points in R2 excluding the origin. The function f given by f of xy equals e raised to xy is the composition of the functions g and h, where g is the function of two variables given by g of xy equals xy, and h is the single variable function given by h of x equals e raised to x. That is, f of xy is obtained by replacing the x in h of x by the expression g of xy. The function g is continuous on R2 since it is a polynomial. And the function h, which is the natural exponential function, is continuous on R as you learned in Math 21. So h is continuous on the range of g. And thus, f is continuous at all points in R2. As a consequence, for any point AB in R2, the limit of e raised to xy as xy approaches AB is equal to its value at AB, which is e raised to a times p. This is the result that we used in the last example in part 1 of this lecture. This is the end of part 3 of lecture 1.2. Before you proceed to part 4, you are strongly encouraged to answer the exercises included at the end of these slides. Thank you for your attention.